Alright, so now we're going to be working on quadratic modeling. This was the last section that we covered in the material of our course, so dealing with quadratic formula, quadratic equations. And so the problem that we're going to work on, which we worked on the other day on Friday, came from section 7.5, problem number 73. So section 7.5, problem 73, and I'm assuming that you can see the table for this problem. So the problem states the capacities at which U.S. nuclear power plants are working are shown in Table 34 for various years. So if you see the data, so 1975, 56% of them were working, of the plants were working at capacity. So at capacity means they're working as hard as they can. So 56% of the nuclear power plants in America were working at their full capacity. Okay, so they give us an entire data set and they say find F of t where F is the capacity in percent at which US nuclear power plants are working at T years since 1970. Okay, now I'm going to admit that at this moment I am kind of modifying the problem a little bit. Question number A, they actually hand you an equation that the book got by doing a quadratic regression, but I want to go through the steps of doing the quadratic regression since that's something you probably need to know how to do for the exam. So I've already loaded the data set into the calculator here. And so 5, 10, 15, 20, and then different values, percentages. So remember that T is number of years since 1970. So 5 would be 1975, 10 would be 1980, etc. And then on this side, this is going to be the percentage of the U.S. power plants working at capacity. So 56% of the U.S. nuclear power plants are working at full capacity, whereas here in 2004, 89% of them are working at full capacity. All right, so we want to find f of t where f is the capacity. So to do that, we're going to do a quadratic regression. So I'm going to go to Stat, Calc, and quadratic regression, you see it as option number 5. And like all the regressions, it's going to ask the same question. What data do you want to do regression on? We'll list 1, list 2. Where do you want to store the equation? And we'll look down here and we'll say vars, yvars, function, y1 as always. And then we'll go ahead and calculate. Okay, so here's the equation. So remember the quadratic equation has y equals ax squared plus bx plus c, and the leading coefficient for a is 0.027. So say f of t equals 0.027 t squared plus 0.216. And that's just going to be t. And then last, 53.295, or 297.6 if we round up. 53.297. Okay. And then let me go ahead and look at my graph. So I'm going to hit zoom 9. So here's data, and here's my quadratic curve. And actually seems to be doing pretty good. There's a little bit of error in a couple of these values, but that's okay. We kind of expect some error to exist in our data set. Although we do recognize that at some point the capacity will reach 100%, so it probably, like parabolas tend to open up and they keep going up forever. Eventually this would probably hit some capacity and level out. And the parabola won't do that, but it will do good to make some estimates, some small amount of extrapolation. So we'll go ahead and run with it. So the next question is, estimate at what capacity U.S. nuclear power plants were working in 2006. Well, the first thing we need to note is that 2006 is 36 years since 1970. So T in our problem is 36. So I'm going to insert the value 36, so 0.027, parentheses 36 quantity squared, plus 0.216 times 36, and 53.297. Okay, and then I'm going to let the calculator do this. Actually, so to do this, I'm actually just going to go ahead and go hit second graph and look at my table values, because it'll give me all the different outputs. So all I need to do is scroll down here. To number 35, or 36, excuse me. Yes, the software on the computers. It's really nice having an emulator, but it does run slower than your calculator probably would. And almost there. 32, 33, 4, 35, and then 36. 96.15. So that is 96.15. All right, and so what type of value is this? But remember, the output is the percent of U.S. nuclear power plants, so power plants, working at capacity. So 96%, working towards 97. Okay. So then the next question is, predict when the U.S. nuclear power plants will be working at full 100% capacity. So when will 100% of the nuclear power plants in America be working at full capacity? So this value, 100%, this is an output value. So basically saying what input, what t value gives me 100%. So I need my equation here. Okay. So now I'm trying to find when this is equal to 100. Okay. So remember, right now the goal is to get everything on one side so that it equals 0. And then, so first step, second step is to use the quadratic formula. And it'll tell me what the t values make it equal to 0. All right, so I need to just subtract the 100 from both sides, so I get 0.027 t squared plus 0.216 t plus 53.297, subtract 100, that equals 0. Okay, so I need to figure out here 53.297 minus 100 is, so 46.703 equals 0. Okay, 0.027 t squared plus 0.216 t. Okay. So now this next part is important. So what do we do now? We're going to use the quadratic formula. So first of all, the quadratic formula states then in this case t equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Those t values will give me 0. So my a is 0.027 and b is equal to 0.216. Your c is negative 46.073. So t is equal to negative 0.216 plus or minus the square root of 0.216 squared minus 4 times the a value, which is 0.027. I've got to squeeze this in here. So c, which is minus 46.073. That's all over 2a. Now remember, you have that program called for that can do the next steps for you, but I do not, so I just need to type this in. So I need so my equation goes negative b, so negative, so parentheses for my numerator, negative 0.216. Okay, plus. I can't do plus or minus, but I could say plus and then square root, so second x squared. So it gives me a square root symbol here. And then parentheses, make sure you put the parentheses in. 0.216 quantity squared minus 4 times a, which is 0.027, times c, which is negative 46.703. Okay, close parentheses. Okay, so that's my radicand. Now I'm going to close one more set of parentheses. This is closing off my numerator. And now I divide it by, and then parentheses for my denominator, 2 times a, 0.027, close parentheses. So that's a lot there. Close one more parenthesis. And we get 37.7, so we'll call that 37.8. So t is equal to 37.8, or t is equal to, so now we have to do this again, negative 0.216 minus the square root of all that, all over 2a. And so that's actually really easy to do once you've typed it in once. It's really easy to pull it back up. You say second enter, and gives me the whole thing I just typed. If I say second arrow to the left, it pushes me all the way to the front. And I just need to go over that plus sign and just overwrite it with a minus and push enter. It's negative 45.8. Negative 45.8. Okay, well, t represents time, and I'm not really interested in negative time because that's basically 45 years before 1970. So not really talking about nuclear reactors back then. And that leaves us with 37.8. So we would say something like this. We estimate that 100% of the power plants will reach full capacity okay, in 37 years since 1970. So that's going to be in 2007. All right. So that's our big answer, 2007. Okay, which leads us really quickly to the last section, which says the last U.S. nuclear power plant to be built was operational in 1996. Explain why it's not surprising that in 2004 applications were filed to build 3 new nuclear power plants in the United States, noting that it takes 4 years to build one. Well, we've already estimated that in 2007, all of our nuclear power plants are going to be at full capacity. So if you want more power, you're going to have to build more power plants. So in 2004, they commissioned for there to be more nuclear power plants so that in the next year, after 2007 and 2008, there'll be 3 more nuclear reactors that they could use, and they would not be working at full capacity. So we needed more power, and so that's what they did. So that's a good kind of cap off to the problem. All right. So the main goals in this one is understanding how to make an estimation and then using the quadratic formula to solve for a given time. So hopefully that will help you for the exam.